So we continue our discussion on the instabilities in the interface of two fluids. Okay, and as previously we saw that finally using plane wave type of solution for the perturbations, we got two equations. One is I times minus omega plus k capital U times A is equal to minus k capital C. Another is I times minus omega plus k U prime times A is equal to k times C prime, capital C prime. These two equations are obtained from, substituting in the basic equations where we equated the Eulerian, velocity component in the z direction, okay, and the Lagrangian velocity component of a fluid particle situated at the same position, okay, both for the fluid above and for the fluid below, if you remember correctly. Then using all these things, finally we got these equations, and we said that we have now two equations but three unknown constants. Okay, so of course we cannot completely eliminate three constants from these equations, so we need any other supplementary or additional equation or relation between this A, C and C prime. Okay, so this condition is obtained by considering that the pressure is continuous across the interface. This is a very crucial consideration. If pressure is not equalized across the interface, then the interface will be ruptured or the distorted. That we don't know. There can be smooth perturbations, there can be curves, okay, but very small perturbation, so it cannot rupture or it cannot damage the interface. The interface should be the interface should not be affected by the whole perturbation process. Okay, that is the whole story behind it. So the pressure should be continuous, and if the pressure is continuous, then we have to look back when we derived some generalized type of Bernoulli theorem, if you remember this type of thing in the equation Roman 4, and we said that this is true for any points in the flow field in our case, because the vorticity is identically 0 for this fluid, and if this is the case, then we can write P is equal to, for any fluid we can just using that equation Roman 4, we can use P, we can write P is equal to minus rho within bracket minus del phi 1 del t plus v square by 2 plus g times xi 1 plus rho times ft. Okay, of course here do not forget that rho is just a constant, and g is the gravitational acceleration, xi is the displacement. So this is actually giving the proxy for the gravitational potential. Okay, so not proxy, this is now represents the term of the gravitational potential. Okay, so you can easily also understand that this is true for any point, that is true. Now we are interested for our current analysis at z is equal to 0, that is the interface, and we can write the pressure balance equation. So for pressure balance equation, this is the pressure, okay, at interface due to the fluid below the interface, and this is the pressure at interface due to the fluid above the interface, and so exactly not exactly that is a bit what I said is a bit problematic, because k is there. So actually the pressure here should be equal to all the same type of expression with the primed coordinate, but here actually a part of the pressure, okay, with the unprimed coordinates is equal to a part of the pressure with primed coordinates plus k, and this k, capital K, contains rho f times t minus rho prime f prime t. These algebraic steps you can do easily. Okay, please check that. Now, if we suppose that the perturbation is only considerable near the interface z is equal to 0, then of course for z tends to infinity, whether this is plus infinity or minus infinity, all the phi 1 prime and xi 1 would vanish, and then basically what we get is the original or initial steady state. That means v is equal to u, capital U, v prime is equal to capital U prime, so they are constants, and all the perturbed quantities are 0. In that case, this is 0, this is 0, this is 0, this is 0, this is non-zero, this is non-zero, and this one is non-zero. So now how much this is, for that you can just do a calculation, and you can simply see that at initial condition or initial state, k should be equal to simply half rho capital U square minus half rho prime U prime square, right? Because if all these four terms are 0, then k will be just here, and then it should be equal to half rho v square minus half rho prime v prime square. Okay, and v is now u and v prime is u prime. Okay, so we have this relation capital G. Okay, now remember, what is the total velocity in general? That is the initial velocity u x cap minus gradient of phi 1. This is the part of the velocity v1, if you want to write like this. Okay, then the square of this will simply be equal to u square minus 2u del phi 1 del x. So it will simply be u x cap dot gradient of phi 1. Okay, of course with a minus sign here. So that will give you like this type of thing, but that will appear twice. That's why you have a 2 factor, and plus there will be a term which will be square of this term, and that will be neglected simply because this is first order term and the square of this will be second order term. So we just keep up to first order term. Okay, now replacing the expression of v square, this expression v square, in equation f, okay, what we can get is this. Okay, because here for obtaining this one, you have to use the expression of k. First write the expression of k which you obtain from G, and finally you replace v square by this expression. If you write, you will see that the term with u square in k will be cancelling the terms in u square which comes due to v square and v prime square. Okay, if you do that, finally you have a compact relation like rho times minus del phi 1 del t minus u times del phi 1 del x plus g times xi 1 is equal to rho prime times minus del phi 1 del t minus u prime del phi 1 del x plus g times xi 1. Okay, you can easily see this one is exactly equal for both the cases. Okay, because when the interface is plucked, let's say from here to here, okay, both the fluid particles which are infinitesimally above and below the interface, both are lifted by the same distance xi 1. Okay, and also both are lifted against G. Okay, so that's why this term is similar, but of course do not forget that this is multiplied with rho prime and this is multiplied with rho. Okay, this type of subtleties should not be neglected. Now finally, if we write the trial solutions in C and D, that means these solutions, this 2 and this solution, and if we replace all these solutions in our newly obtained condition due to the pressure balance at the interface, okay, we finally get a relation, super interesting relation like rho times minus I times minus omega plus k capital U times C plus G times capital A is equal to rho prime within bracket minus I within bracket again minus omega plus k times capital U prime times C prime plus G times capital A bracket closed. So this is the pressure balance condition. So finally our purpose is served. We have obtained another algebraic relation between C, A and C prime. So now we have three equations. This one J and the other two are here in capital E. Okay. And now we can totally eliminate all these constants of integration. I mean, they are not constants of integration, all these constant amplitudes of the perturbation to obtain the relation between the frequency of each Fourier mode and the corresponding wave numbers. Okay. So if you do that correctly, so this homework is I ask you to do. Every one of you should do this. This is a doable homework. A bit 2 or 3 steps are there, but if you do systematically, you can easily get there. Okay, so this dispersion relation finally comes out to be rho times minus omega plus k times capital U whole square plus rho prime times minus omega plus k U prime whole square is equal to kg rho minus rho prime. Okay. So just think that if the two fluids are having very matching, very close density, then this is the order of 0, right? Then what happens to this dispersion relation? For example, if U and U prime, they are same, then what happens to this dispersion relation? Okay, so think whenever in physics you obtain some analytical relation, try to understand different type of limits. If your analytical result is correct, okay, there is no problem in it, in calculation or in assumptions, then it should give you correct results or intuitive results in the known limits. Okay, so that I leave for you to check and verify. Okay, if you have any question, of course we can discuss in one of the in any session. Okay. So yeah, up to this, so this equation number k is the parent equation of all our following discussions. So this is what? This is nothing but the dispersion relation of the linear wave mode. If the dispersion relation's frequency can be written in this way, so of course you can easily understand that if we consider that the wave vector is given, then this is nothing but a quadratic equation for omega, and omega can be written in this way, that omega by k is equal to rho capital U plus rho prime capital U prime by rho plus rho prime plus minus this whole factor. That means g by k rho minus rho prime by rho plus rho prime minus rho prime U minus U prime whole square by rho plus rho prime whole square whole to the power half. And you can easily understand that rho is positive, rho prime is positive. According to our construction, both U and U prime, they are positive. So this is positive. Okay. And not only that, actually U and U prime, even they are even some of them are negative, doesn't matter. Finally, you can easily check that the omega at least that can be real. Okay, so whether this is positive or negative, that actually can be observed in its dispersion relation with k sometimes. Okay, so that's another thing, but at least here for this part there is no chance for omega being complex. This is a real part. Now the question that whether this will give us a stable solution or not, for that we have to check whether under which condition omega has a real value. If it is a real value, then we have a stability condition. If that means the system responds in terms of linear wave modes. If omega has a complex part, okay, which should come from this part, of course you understand that there is a square root and there are two terms. Okay, So the interplay of the two terms will tell us that whether this is imaginary or this is real. Okay. So and if this has an imaginary part omega, then the system will lead to an instability. Okay, of course, linear instability. Now we are just using these equations, we will just discuss very briefly the following interesting cases. So one case is known as the surface gravity waves. So that means that we have two fluids, okay, which are both are initially at rest. That means both capital U and capital U prime, they are 0, and the lighter fluid is resting on the heavier fluid. So rho is greater than rho prime. Okay, so rho prime is the fluid above. Okay, so this one is lighter, this one is heavier. So for that case, what happens to this equation? U and U prime both are 0, so this term goes away. This term also goes away. So we only have this term, and rho is greater than rho prime. So this will be positive, for positive k, of course. This will be positive. So square root of this positive thing will be a real thing. So in this case, we will see that the initial system, the initial condition, the condition that the system is at rest, two fluid system was initially at rest, actually gives birth to a linear wave mode. So any weak perturbation caused to this interface, two fluid interface, would give birth to a linear mode whose phase velocity is, or the dispersion relation is given by m, where omega by k is equal to plus minus root over g by k, rho minus rho prime by rho plus rho prime. Okay. So finally you can see that the phase velocity of the mode is just this. Okay. So for all k, we don't care what is the value of k, omega is always real, since rho is greater than rho prime. Okay. Now it simply says that the disturbance in this case moves on the interface in the form of a linear wave mode, which is called the surface gravity wave. Okay. And here you can see for this mode, unlike the sound speed, the phase velocity actually depends on k. So this is a dispersive wave. Okay. So the phase velocity is not a constant. So it depends on k. Okay. So this is the story of one case. Now, if we just consider a very special case, that's what I say, that it is always good to check the limits. For example, air-water interface. So where rho prime is very less than rho. The density of air is very less than density of water. Air is compressible, but it is true that it is fairly incompressible with respect to the other gaseous things. So reasonably we can approximately use our current framework, that is true. Okay, so if we do that, then finally what happens, this both rho minus rho prime and rho plus rho prime both will be approximately equal to rho, and finally this will get cancelled, and we will have simply omega by k almost equal to plus minus root over g by k. So omega will be equal to plus minus root over gk. Okay. Now surface gravity waves are mainly important for the study of ocean atmosphere interface. Okay, that's in oceanography. For the astrophysical framework, we can have also interesting thing with the surface gravity wave, because in lower solar corona, okay, it is observed actually surface gravity waves are are there, and it is true that then actually we cannot model the whole thing using neutral fluids. Then plasma comes into play, and the surface gravity waves will be a generalized form of this surface gravity waves, which will be the magnetized or magnetoacoustic surface gravity waves, which I will talk a bit later when I will talk about the magnetohydrodynamic waves. Okay. After that, another very interesting thing, so this was the story of a stability condition where the system responds in terms of a linear wave mode. Now we see the inverse situation, but always with the same initial condition. This, by definition, this is another condition which is known as the condition for, case of Rayleigh-Taylor instability or RT instability. Okay. So the initial condition is exactly the same. That means u is equal to u prime is equal to 0. But one thing is changed there. Now whenever you have two fluids, then the relative configurations, okay, or the relative situation of one fluid with respect to the other is very, very important. So here this is true, this is exactly equal to the previous case, but now rho prime is greater than rho. So in that aspect, the initial condition is not exactly the same. And if this is true, then from this equation you can actually see that rho prime is greater than rho, so it must be negative, and so omega should be, okay, omega should be imaginary in the equation M. Okay, so this part will add finally to the instability. Okay, and this is known as the Rayleigh-Taylor instability. Now, just instead of seeing this as a very exotic thing, just think very clearly that let's say I make somehow by force or something, clamping or some setup, two fluids at rest. Okay, where the of course in the gravity field, Earth's gravity field. Now they are rest vertically. So the lighter fluid is below and the heavier fluid is on the upper side. What will happen if we just lift the constraint? So this one will come down and this one will try to go in, right? Of course not in the convective manner, but they will, what will in general do that this fluid, this heavier fluid actually comes down in the structure of fingers, okay, fingertip type of thing. Okay, so it penetrates this fluid gradually so that it finally occupies, it can finally, so the final destination is finally tries to goes down, okay, and below the lighter fluid. Okay, of course this is very interesting case for the fluids in gravity field, which was observed for gravity field by Rayleigh in the year 1883. But this instability can also be found if a lighter fluid accelerates against a heavier fluid. So the gravity field can be any other accelerating field, right? If of course the accelerating field is acting as a conservative body force field, that is something very important. Otherwise that cannot be written as a gradient of some potential function, and the generalized form of the Bernoulli equation cannot be proved easily. And that was done by Taylor. Okay, 67 years later, 1950. Okay, so this is the same Taylor who worked on the Z of Taylor instability during the supernova explosion. Using the blast waves during the Second World War for the atomic bomb explosion. Okay, now this type of Rayleigh-Taylor instability is of much importance for the astrophysicists, because in many instances one can see RT instability. For example, I here just want to mention one very useful one which we have already discussed, that is the very initial phase of supernova explosion. When the explosion just takes place and the explosion does not enter into the self-similar phase, that is the phase of Z of Taylor. Before that, the ejected gas gets out of the center of the explosion and tends to pile up in a thin shell behind the interface. That was observed by Gall in the year 1975. Okay, so the situation is equivalent to a two fluid system where the lighter fluid is below the heavier fluid and the acceleration is outward. So the acceleration is basically due to the energy of this fluid. So the fluid is now piling up here. This is the interface, and here there is very dilute ambient medium. Okay, and so if you just now see that this so if the acceleration is acting in this direction, so with respect to this acceleration direction, okay, so it is exactly equivalent to saying that the heavier fluid is above and the lighter fluid is below. Okay, so we can expect, of course, a Rayleigh-Taylor type of instability, and actually they can see that. So here in this slide I will try to show you different observational instances of Rayleigh-Taylor instability. So one is taken from a paper by Livescu and Balzar in 2015. Okay, so here actually you can see for a for a numerical simulation, you can see that the heavier fluid basically, so this was not really special for astrophysical thing, but just for normal Rayleigh-Taylor simulation. So heavy fluid becomes penetrating in the lighter fluid. Now you see this brownish fingertips. So whenever you see this type of fingertips are coming, this is a clear signature of Rayleigh-Taylor instability. Okay, and of course in this case the two fluids, both of the fluids should be at rest initially, or very low velocity with respect, very low velocity, almost at rest. Okay, otherwise this is not possible. And here you can see this is a picture by Crab Nebula, where you can also see finger type of structures, okay, to the ambient dilute medium, so which can also indicate towards a plausible RT instability. Now finally, for the supernova simulation, this is a very early phase supernova simulation where this is not self-similar and spherically symmetric till now, and you can see that the blast wave material actually tries to penetrate to the very dilute ambient medium just by the virtue of RT instability. Okay, this was taken from a paper, recent paper by Wieland et al. 2019. Okay, now the last one of the lot. After that we will end this discussion. Okay, so the last one is so the so-called Kelvin-Helmholtz instability. So what is that? For Kelvin-Helmholtz instability, we will do like this: u and u prime, we will make them non-zero. But if they are non-zero and they are equal, then again you can see this term will be 0. So we will always have some stability. There is nothing interesting. So we will not only make them non-zero, but make them different. And rho is greater than rho prime. So the system should be already stable in terms of Rayleigh-Taylor instability. So it is the heavier fluid is in the bottom, at the bottom, and the lighter fluid is on the top. But now the fluids, both the fluids are flowing. Okay, both the fluids are flowing with non-zero velocity. That is the initial steady condition, flowing but with uniform velocity. Then what happens? Then of course this will have an imaginary part only when this part is negative, and that is simply true when this part is less than this part. Okay, so just by algebraic manipulation you can see that 1 rho plus rho prime will cancel out, and finally we have rho times rho prime times u minus u prime whole square greater than rho square minus rho prime square times g by k. Okay, and then the k should be, there is now, till now we did not have any k dependence in the criterion of the instability. Now we will have a k dependence. The k should be greater than rho square minus rho prime square times g by rho prime times u minus u prime square. So if my k is greater than this value, I will have a Kelvin-Helmholtz type of instability. And Kelvin-Helmholtz type of instability is also important for solar physics. Maybe I will come to that later. And also in the case where you can see that some flowing river and on just on the river surface some wind is also blowing, then the surface is actually undulating. Okay, and that is the clear signature of Kelvin-Helmholtz type of instability. In case of astrophysics, Kelvin-Helmholtz type of instability can be seen in extragalactic jets, where some fluids are spitted by a galaxy from very localized region in a galaxy and tries to mix or tries to go to the very dilute intergalactic medium. Okay, so here you can see that k is greater than some critical value, means the length scale of the perturbation should be less than to some minimum value. Okay, for the instability, L should be less than some maximum value. Okay, so of course one very important thing in whole treatment, we have we have taken into account the incompressibility for water and air surface we have discussed, but we have neglected the effect of surface tension. Actually, the introduction of surface tension majorly modifies the results, and you can see that then k will have also a, this is the lower bound. Okay, then actually k should, u minus u prime should have another type of bound relating on the, depending on the nature of the surface tension. Okay, so this type of exercise you can actually see on internet, how surface tension can actually modify Kelvin-Helmholtz instability, how magnetic field can modify Kelvin-Helmholtz instability. Those things are subject of very interesting and ongoing research. Okay, so that is something here. I can inspire you to think and just try to do some more general analytical approach. Okay, so in this lecture we have seen analytically how to tackle the instabilities or the very weak perturbation and the response of the two fluid medium, okay, to this perturbation, um, whether in terms of linear modes or in terms of instability. And we actually also discussed that why and in which circumstances Rayleigh-Taylor instability, Kelvin-Helmholtz instability, this type of two fluid interface instabilities are important. In the next discussion, in the next lecture, okay, that I will give next week, I will talk about a very interesting topic which is known as the physics of stellar oscillations. Okay, and actually you can see, it is observed that the luminosity of the stars, including the sun, okay, they are oscillating, so that the luminosity changes periodically. Okay, and in this way actually it is called the oscillation of the sun or the oscillation of the corresponding star. Okay, so and in fact one can easily understand by proper analysis that there is a proper mechanical oscillation type of thing of the stellar body, okay, corresponding to the periodic change in the luminosity. Okay, so that I will discuss in the next week. Okay, thank you very much.